Welcome back to the deep dive. As experts in machine learning, we all understand the critical need for robust AI systems, especially, when we think about things like adversarial attacks. And so today we're going to take a deep dive into a new research paper. And this paper proposes something kind of fascinating. It asks, can we make AI models more resilient by just simply giving them more time to think?
That's right.
Okay.
The paper is titled Trading Inference-Time Compute for Adversarial Robustness.
Okay.
And it's by Wojciech, Zaremba, and others. It explores whether if we increase computational resources during inference, can that lead to better adversarial robustness?
So instead of focusing on adversarial training techniques where we're actually modifying the model itself,
Right.
this research is exploring leveraging just raw computational power during the inference stage.
Exactly. The authors, they think that if you give the model more time to kind of process information and reason through how it's going to make its decisions, that it might be able to overcome those subtle manipulations that are introduced by adversarial attacks. And they chose to test this using OpenAI's large language models, the O1 Preview and the O1 Mini, because these represent kind of the state-of-the-art in natural language processing.
Interesting choice. Now, for our listeners who might not be as familiar with the nuances of adversarial attacks, could you give us a quick overview of the types of attacks that the researchers tested in this paper?
Sure. The paper focuses on evaluating the impact of increased inference time on a whole bunch of different attacks, including ones that are designed to cause misclassifications and ones that target kind of specific reasoning tasks.
Okay.
The attacks that they test kind of fall into a few categories. The first is attacks based on word substitutions. So that's where the attacker will try to mislead the model by replacing specific words in the input text.
So, for example, subtly changing, like a positive sentiment word to a negative one in a product review.
Exactly.
Try to manipulate the model's overall sentiment classification.
That's right.
Okay.
And they also examine the effectiveness of synonym replacements. And so here, the attacker will substitute words with their synonyms, aiming to keep the grammatical structure of the input the same, but altering its meaning.
I could see how that would be particularly challenging for a model to detect.
Right.
Did they explore any other categories of attacks?
Yeah, they also investigated attacks that involved injecting irrelevant or distracting information into the input.
Okay.
So the goal here is to kind of overwhelm the model with noise and divert its attention from the really crucial information, and that might lead to a decline in performance.
It sounds like they covered a comprehensive range of attack types.
Yeah.
Now, let's get to the heart of the matter.
Yeah.
What did they find? Did increasing the inference time actually improve the model's robustness against these attacks?
The results were surprisingly compelling. The researchers discovered that increasing the inference time did lead to notable improvements in adversarial robustness against a lot of the attacks that they tested.
So giving the models more time to think did translate to better defenses.
Yeah.
Could you elaborate on the extent of those improvements?
Sure. One of the most striking observations that they made was that a lot of times the success rate of these attacks would tend towards zero as the amount of compute or inference time was increased.
That's significant. That suggests that there's a direct correlation between giving the model more time to process information and its ability to resist adversarial manipulation. Are there any specific examples from the paper that highlight this effect?
Absolutely. So, for example, they found that attacks based on word substitutions where, specific words were replaced to try to mislead the model, they were particularly susceptible to the benefits of increased compute.
That makes sense.
Yeah.
If the model has more time to analyze the text that's been altered, it's more likely to identify semantic inconsistencies introduced by those word substitutions.
Exactly. And similarly, attacks that relied on introducing irrelevant or distracting information,
Okay.
those were also mitigated by increasing the inference time. So the model, with that additional processing time, it could kind of filter out the noise and focus on the information that was most relevant for whatever task it was doing.
It reinforces the idea that increased computational resources can act as a buffer,
Right.
allowing the model to perform a more thorough analysis and overcome those deceptive elements introduced by the attacker. However, I'm curious, were there any situations where increased compute did not result in improved robustness?
Yeah, that's a really important point. And the paper does acknowledge that there were certain types of attacks where just increasing the compute, it didn't lead to any improved robustness.
That's interesting. Could you elaborate on those specific types of attacks and why they might be more resistant to the benefits of increased compute?
The attacks that proved more resilient, they tended to be the ones that targeted the model's underlying logic, or they exploited very specific reasoning flaws.
So even with more time to process the input, the model was still susceptible to attacks that targeted fundamental weaknesses in its reasoning capabilities.
Precisely.
Okay.
And this suggests that while increasing inference time can be a very powerful tool for enhancing robustness, it's not a universal solution. There are inherent limitations that compute alone can't address,
Right.
especially when you think about fundamental flaws in the model's logic or its training data.
That makes sense. It's like giving someone more time to solve a math problem.
Yeah,
If they don't understand the underlying concepts, no amount of additional time will guarantee a correct solution.
exactly. So while this research demonstrates the potential of increased compute for enhancing AI robustness, it also underscores the importance of continuing to explore other approaches, like robust training techniques, just to address those more fundamental weaknesses in AI models.
Absolutely. It seems like the key takeaway here is that compute can be a valuable tool in our quest to build more secure and reliable AI systems, but it's essential to understand its limitations and use it strategically in conjunction with other approaches.
Exactly. This research provides valuable insights for developers and researchers who are striving to build AI systems that can withstand those increasingly sophisticated adversarial attacks that we face in today's landscape.
It certainly raises some fascinating questions, and it opens up new avenues for research. Let's dive deeper into the specifics of the experimental setup and delve into some of the more nuanced findings in the next part of our deep dive.
Welcome back to our deep dive into trading inference-time compute for adversarial robustness. We've sort of established that the core idea of the paper is that increasing compute during inference might make large language models more robust.
Right.
So now let's unpack the specifics of how they set up their experiments so we can understand how they got to these findings.
Absolutely. The methodology is key to understanding the validity and the applicability of the results. Could you walk us through the experimental design?
Sure. So the researchers decided to focus on two large language models for their experiments, OpenAI's O1 Preview and O1 Mini.
Okay.
And they picked these models because they represent, state-of-the-art capabilities in natural language processing, which makes them good test subjects for figuring out how compute impacts adversarial robustness.
Makes sense. Given the focus on language models, what specific tasks were these models evaluated on?
So the tasks that they were evaluated on were chosen to represent a bunch of the common ways that large language models are used. So things like text classification, where the model has to categorize some given text into, categories that have already been defined.
Okay.
And then also question answering, where the model needs to take a question and then extract the answer from some given text.
So tasks that require kind of a deeper understanding of the language and the
Correct.
context. Now, getting back to the core focus of the paper, how did they manipulate the inference time or the compute that was allocated to these models?
So they use something called beam search decoding during the inference process. And beam search is a pretty widely used algorithm for decoding sequences, especially in language modeling.
Okay.
And by changing the beam width parameter, they were able to actually directly control how much compute was allocated to the model while it was doing inference.
Can you elaborate a bit more on how beam width relates to compute?
Sure. Beam width basically determines how many candidate sequences the model looks at every single step of the decoding process. So a bigger beam width means that the model explores a wider range of possibilities, but that takes more computation.
Okay.
But if you have a smaller beam width, then the model can only look at kind of a smaller number of things, and so that's faster, but it might not be as accurate.
So by manipulating the beam width, the researchers could control that trade-off between how long inference takes and how thoroughly the model searches.
Exactly. And this let them really systematically evaluate how increasing the compute or the time the model has to think affected its ability to resist being tricked by these adversarial things.
Now let's get to the adversarial attacks.
Mm-hmm.
You mentioned earlier that the paper explored a bunch of different categories of attacks.
Yeah.
Can you remind us of these attack types and maybe give some specific examples of how they were implemented?
Yeah. So as we talked about before, the attacks that they tested can be grouped into three main types. word substitutions,
Right.
synonym replacements,
Yep.
and then injection of irrelevant or distracting information.
Right. Could you walk us through each of those, maybe with examples from the paper?
Okay, sure. So for the word substitution attacks, the researchers used special algorithms to replace words in the input text with other words that mean almost the same thing, but that were chosen to try to trick the model. So, for example, in a sentiment classification test, you might replace a positive word like excellent with a less positive word like decent to try to make the model think that the sentiment is not as positive.
So subtly shifting the meaning without changing the grammar too much.
Exactly.
What about the synonym replacement attacks? How did those work?
So the synonym replacement attacks, those involve replacing words with their synonyms. And again, the goal here is to keep the grammar the same but change the meaning. For example, in a question answering task, you might replace a really important noun with a synonym that has a slightly different meaning or changes what the question is focused on.
Uh-huh.
And that could lead the model to give the wrong answer from the text it's given.
I can imagine those subtle shifts in meaning would be tough even for humans to catch sometimes.
Yeah.
And what about those attacks where they add irrelevant or distracting information? How did they do that?
Right. So for those attacks, the researchers basically just added extra words or phrases to the input text, and these words and phrases were designed to distract the model from the important information. So imagine if you took a news article and just added random sentences from a totally different topic. The model would have to figure out how to ignore all that extra stuff and find the actual important content.
It sounds like that would be pretty hard for any language model.
Right.
So they had all these different attacks, each one made to exploit a different weakness in the models.
Right.
Now, how did they actually measure how well the models did at resisting these attacks when they increased the inference time?
So they did it very systematically. For each type of attack, they made a bunch of adversarial examples by applying the attack algorithm to the original input data.
Okay.
And then they gave both the original inputs and the adversarial examples to the models, but they changed the beam width each time.
So they tested the models on both clean and adversarial data under different compute conditions. What metrics did they use to evaluate the robustness?
So they mainly focus on two things: accuracy and attack success rate. So accuracy, measures how often the model gets the right answer.
Right.
And attack success rate, that measures how often the attack actually tricks the model into getting the wrong answer.
So they were looking at the overall performance of the model and how easily it could be tricked.
Exactly. By comparing the accuracy and the attack success rate under different beam widths, they could see how much of an impact increasing the compute had on the model's robustness.
It sounds like a very thorough and well-controlled experiment.
Yeah.
Now, the key question, what did they see? Did increasing the inference time through the beam width actually help the models do better against these attacks?
Yeah, so the results, as we talked about a little bit before, were pretty interesting. They found that across a lot of the different attacks and tasks, there was a clear trend. When they increased the beam width, and therefore the compute that was used during inference, the models got better at both accuracy and attack success rate.
So giving the models more time to think did actually mean they were better at defending themselves. Can you talk a bit more about how big those improvements were and any patterns that they noticed?
Yeah, sure. So they found that the improvement in robustness, it kind of depended on the specific attack and the task. For example, attacks that relied on subtle changes to the input, like word substitutions or synonym replacements, they were more likely to be stopped by the increased compute. In a lot of cases, the attack success rate for those attacks dropped way down as the beam width went up.
That's in line with what we thought earlier. If the model has more time to look at the input, it's more likely to see those small changes that are trying to trick it. Were there any types of attacks where the effective compute wasn't as big?
Yes, as we've said before, attacks that targeted the way the model actually reasoned or used specific weaknesses in the training data,
Okay.
those tended to still work even with more compute. Even when they had more time, the model could still be fooled by these kinds of attacks.
That supports the idea that compute is a good tool, but it's not a perfect solution.
Right.
It shows that we need to think about AI security in many different ways, looking at both the compute side of things and the underlying weaknesses in the models themselves.
Exactly. This research helps us understand the complicated relationship between compute and robustness. And that's really useful information for developers and researchers as they work on making AI systems more resilient.
This is fascinating stuff. I want to dig into the specific results and talk about what they mean for the future of AI security.
Okay.
Let's continue exploring this in the final part of our deep dive. Welcome back to the final part of our deep dive into trading inference-time compute for adversarial robustness. We've talked about the main ideas, the attacks that were tested, and how the experiments were set up to look at the connection between compute and robustness.
Right. We've seen how giving the model more time to process information by changing that beam width parameter can really help a language model resist certain kinds of attacks.
Now let's look more closely at the actual results that were in the paper. We know that they found that more compute often led to better robustness. Can you tell us a bit more about how big those improvements were, maybe with some specific numbers from the paper?
Sure. The paper has a lot of detailed results for different tasks and types of attacks. One of the interesting findings was how much compute helped with word substitution attacks. For example, in a task where the model had to classify sentiment, they saw that the attack success rate dropped from about 80% with a small beam width to almost 0% when the beam width was much larger.
Wow, that's a huge improvement. So basically, the model was pretty much immune to those word substitution attacks when it had enough compute.
Pretty much, yeah. And they saw this trend across a lot of different tasks, which suggests that when the model has more time to process the input, it can figure out and get past those small manipulations.
Were there any other really interesting results or trends that stood out to you?
Yeah, they talk about something they call the threshold effect, where sometimes a small increase in compute led to a big jump in robustness.
That's interesting. Can you explain what that means and why it's important for designing robust AI systems?
Sure. The threshold effect means that there might be certain levels of compute where you get the biggest improvements in robustness without needing a ton of extra computational power. This is really important in the real world because it means we might not need huge amounts of compute to make our systems much more robust.
So it's about finding that balance where we're getting the most benefit in terms of robustness without overspending on computing power.
Exactly. It shows that we need to be smart about how we use our computing resources for AI security.
This paper was focused on large language models. Do you think these findings could also apply to other types of AI, like those used for computer vision or robotics?
That's a good question, and it's something that needs more research. The paper looked specifically at language models, but the idea that more compute can make systems more robust might be true in other areas too. But more research is needed to see if that's the case and what challenges might come up in different areas of AI.
It seems like this research challenges the idea that we should mainly focus on robust training techniques or changing the way AI models are built to make them more robust. Does this mean we should shift our attention to compute as the main solution for AI security?
That's something important to think about. This research shows that compute can be a really useful tool for making systems more robust, but we need to be realistic. Compute isn't a magic solution. It works best against certain types of attacks, especially those that use subtle changes to the input data.
Right, like we've discussed, those attacks that target how the model thinks or use specific weaknesses in its training data might still work even with more compute.
Exactly. We still need robust training techniques and changes to how AI models are built to address those more fundamental weaknesses.
So it's not about replacing those methods, but adding compute to our toolbox and using it along with other techniques to make our AI systems more robust.
Right. This research tells us that we need to think of compute as a key part of making AI secure and explore how to use it best with other approaches.
This paper has been getting a lot of attention in the AI world. What are some of the main takeaways you think researchers and developers should keep in mind going forward?
I think one of the biggest takeaways is that we need to be more thoughtful and consider the context when we're thinking about AI security. The relationship between compute and robustness isn't always straightforward. It depends on the attack, the AI model, the task, and a lot of other things.
So instead of trying to use a single approach for everything, we need to carefully consider the specific weaknesses of each AI system and design defenses that fit those weaknesses.
Exactly. Another important takeaway is that we need to keep researching how compute actually contributes to robustness. We need a deeper understanding of why it works so we can come up with better strategies for using it to make our AI systems more secure.
This research has opened up new areas to explore and given us valuable insights that will shape future research in this field. It seems like building robust AI is a journey, not a quick fix.
Definitely. As AI systems get more advanced and are used more in our lives, the threats they face will also get more complex. The research we've talked about today is a big step forward in that journey. It gives us new ideas for building more reliable and trustworthy AI in the future.
Thank you for joining us on this deep dive. We hope you learned something new and interesting. Until next time, keep exploring the amazing world of AI.